So a glass is a liquid that's lost its ability to flow, pure and simple. Why has it lost its ability to flow? Because as the temperature goes down, the molecules move more and more slowly, and you have to detect their motion with some type of experiment which has got a time scale. And when the molecular motion time scale crosses the experimental time scale, the system falls out of equilibrium, and you have a glassy state. So you can make a glass on a very long time scale, or you can make it on an extremely short time scale, as one would do with these droplet cooling experiments, for instance. So it's rather arbitrary. In the old days, the glass was determined by reaching a viscosity of 10 to the 13th poise, which was a reproducible number. But these days it tends to be more measured in terms of where a simple differential scanning calorimeter will pick up a jump in heat capacity as the liquid-like degrees of freedom become activated, and that time scale is about 100 seconds. As a consequence of interesting glass formation in aqueous solutions, because these measurements in aqueous solutions are always pointed towards something special which has been called the glass transition of water at a particular temperature of 136 degrees Kelvin, which is where people working with pure water had assigned it also. And this is where the problem became, because we know what the entropy of fusion of water is, and we know what the heat capacity of water is around 0 Kelvin. And if you extrapolate that heat capacity and you integrate it using the formula for excess entropy, you find that this substance, supercooled water, would run out of entropy, nothing left to lose except vibrational entropy, at a temperature which is well above this so-called glass transition temperature. That's a big problem. In nearly all normal glass-forming liquids, when you make this extrapolation, you get to the glass transition and there's still an excess entropy left. The residual entropy of glasses, as is famous to talk about. So here was this most important of all liquids, not conforming to what we were used to from supercooled liquids. So immediately there was a puzzle. The natural thing to do was to think that the heat capacity function that we're integrating over was wrong, and that instead of just going flat the way other liquids did, it should take a nosedive to a smaller value so as to postpone the loss of entropy until a lower temperature below the glass transition temperature. So we said, well, we must measure this heat capacity. And so we started work on measuring heat capacity, expecting to see this decrease, and lo and behold, what we saw was exactly the opposite, the rapid increase, which meant the problem was getting worse. This is the history. And then it was with this increase in mind that Robin Speedy, coming from an ionic liquids background in New Zealand, stumbled into our laboratory, most welcomely, and looked at this and said, we should measure the compressibility. Well, we both said we should measure the compressibility, and this is when the increase in the compressibility, mirroring what we'd already seen in the heat capacity, came into play. And the masterstroke of Robin was to fit it with a power law, with a singular point, and then to take this fitting to other properties which are available, including many of the transport properties, and finding they all fitted this power law with the same singular temperature. That's how it came in, and this took about 3 years to publish Robin's paper, but because it seemed nobody wanted to believe this. But that's where the real scientific interest, physicists as well as chemists, came into the picture. Is it possible to consider a liquid, how did we put it actually, the existence of vitreous polymorphs? In other words, two different structures of the same material that could coexist in equilibrium at least for some distance and temperature above the glass transition temperature. But we were so sure that our paper would be rejected if we put this into the body of the paper that we put it in a footnote. And it's there for history said to record because it's very much what we think we're seeing now in these days, where there's evidence from various workers that you can indeed have a liquid in two forms that can coexist, at least for a given length of time. So that was, I think, the first time that possibility was mentioned. I've told you about Robin Speedy and myself having two competitive views of interpreting the power law divergences. And the paper we published contained both of them, one of them being a liquid approaching the edge of its free energy surface, and the other one, which was Robin's spinodal interpretation. And I preferred something internal to water, namely a bump in the free energy surface. And then Robin, after he went back to New Zealand, published a wonderful paper. I remember reading it in draft form and having shivers going up and down my back because it was so deeply perceptive. And this is his famous conjecture paper, the stability limit conjecture, in which he connected the spinodal limit to high temperature liquids approaching the well-known critical point to the spinodal limits which came from his power law fits to the compressibility in other subjects through an intermediate stability limit range which he used as a basis for developing an equation of state for water which contained the stability limit. So he got the famous continuous spinodal, and that paper was, I think, the state of the art in interpreting the properties of supercooled water from 1982 when he published it, until computer simulations became powerful enough to be brought to look for the speedy spinodal. And that was being done in the laboratory of Gene Stanley in the hands of Peter Poole and Francesco Shortino, who you've just mentioned. And they were specifically looking for divergences in the simulations, and what they found instead, using this particular pair potential, the ST2 potential, was that instead they found the indications of a Van der Waals-like loop implying the existence of a second critical point between two liquids. And their paper, published in Nature in '92, then started this frenzy of interest in water in terms of a second critical point, which has remained controversial. And then from '92 to where are we at now? Nearly 22. So for 30 years, that's been a focus of controversy. But it's becoming more and more, I think, plausible now that some of us, namely the man in front of me, learning how to penetrate no man's land. What do I mean by no man's land? I mean the barrier to direct experimental measurements of spinodals and critical points, which is imposed by the crystallization of water to ice. So you try to answer the question by getting closer and closer to this divergence temperature, and it becomes more and more difficult to exclude crystallization. And once the crystals start, of course, the system reverts to its stable form, and you cannot do any more measurements. So the challenge has been, how do you overcome this crystallization barrier? And there are a number of answers to that. Some people answer it by the way Anders Nilsson and his colleagues have been doing it, by using ultra-fast experiments to probe what happens below the melting point, below the normal crystallization temperature. And other people have done it by, attempted to do it by coming from below, by raising the temperature extremely fast into no man's land. And then still others, but again, Anders, coming sideways from high pressure in recent experiments, which I enjoyed listening to, hearing about very much. And then there are thermodynamic approaches where you can assume that the behavior of water at temperatures in the glassy state and just above the glass transition temperature are continuous with those above, and you can apply thermodynamic laws to exclude certain behaviors within the experimental errors and deduce how the heat capacity must be behaving in between. And then, of course, there are modeling experiments, two-state models, which are pretty powerful, which also will give you interpretations which are consistent with the data and tell you the rest of the story, what must be happening below the crystallization temperature. A number of different ways, and to an extent there's quite a lot of consistency in what they're finding. And the picture's becoming clearer and clearer. Not completely clear yet, I think you agree, but it's very close.